Okay, so let's take a look at Chapter 4, things you need to know for your unit exam. The first thing there is a figure from your textbook that you can kind of see. It goes from solid, the little circles have water as a solid, water as liquid, and water as vapor. And then kind of going from left to right, we actually need to add energy for ice to melt, and we need to add energy for liquid to vaporize. And it's hard to see probably, but there in red actually is how much energy. So you have 80 calories in the case for melting solid to go to form a liquid, and 600 calories for a liquid to go to form a vapor. So, and actually kind of, we know that ice can go straight to a vapor. We call that sublimation, and that takes 680 calories. So that's energy is required, is kind of the big crux there. And then going from right back to left again, that would be energy is actually going to be released in those cases. That is when a gas condenses and 600 units of 600 calories are released. And as water goes from a liquid to a solid, energy is also released. So I think on your exam it's something about when is what phase change, because these are all different phase changes, the liquid, solid, and gas. What phase change is most energy released, and it's during condensation. I think that's what it is anyway. The hydrological cycle is basically the water cycle, and going back and forth specifically between the atmosphere and the geosphere. And so kind of summarized the main the main source of getting liquid water into the atmosphere is evaporation. Of course, the water needs to condense, and then the water will fall from the atmosphere back to the geosphere via what we generally call precipitation. The next two, actually, we can talk about that same figure. We talk about a parcel of air and how do you say how much water vapor there is. Mixing ratio and absolute humidity, both isolated chunk of air. And they talk about, in both cases, the grams of water vapor, but in the case of the mixing ratio, it's grams of water vapor per kilogram of dry air. In the case of absolute humidity, it's grams of water vapor per volume, or 1 cubic meter. Saturation and equilibrium, I brought in these figures from your textbook. Kind of from left to right, you see basically the first chamber is there's no water vapor in the air, in the headspace above that liquid. I kind of think of it as like removing a film or a piece of saran wrap. And then right away you can go ahead and have evaporation into the chamber, into the headspace above the liquid water. Notice in this case actually there's much more evaporation than there's one condensation there in the middle kind of chamber, or in the middle figure. In that last figure, the third figure, actually at that point finally we actually have both evaporation, that's liquid going to a gas, and condensation, the gas going back to a liquid. And if you were to count the number of particles, actually that is the rate of evaporation is equal to the rate of condensation. That's what we call equilibrium, and that's a situation that the air, the headspace above that liquid, is what we say saturated with water vapor. And the old adage that warm air holds more water vapor than cold air, actually there's something to be said for that. There's a table that talks about the saturation mixing ratio at the different temperatures. And indeed, the higher temperatures will hold more water vapor. The saturation mixing ratio increases with temperature. Relative humidity, RH. Basically, it's how close the current air is to reaching saturation. And there in blue, I've kind of said in general how you do that. Basically, you have to measure the water vapor in the air, and then you divide that by the amount of water vapor to be required at that temperature. So the bottom number actually you get from a table. Relative humidity, how it changes over a 24-hour period. So what we've got there is a couple figures from your textbook. The red line is looking at the daily temperature. Of course, we have the minimum temperature right before dawn. The highest temperature we said was like 2 or 3 p.m. The bottom line there is the relative humidity. And so notice that actually at the highest temperature, about 2 or 3 p.m., that is actually our lowest relative humidity. And that's a little bit counterintuitive. But remember that warm air will hold more water vapor. So assuming that there's the same amount of water vapor present, then its relative humidity is actually at its lowest. Relative humidity will be at its highest right before dawn. That's why when you go camping you get wet. You feel kind of miserable about dawn. A sling psychrometer is one way to measure relative humidity, and basically there are two thermometers. One has like a little fabric around it, so you can dip it in water and wet that sock. And the other one, the other thermometer doesn't have a sock. So if you go ahead and wet, especially the one with the sock, you could wet them both if you want, but the one with the sock actually, if you aerate it, there will be a cooling effect in the liquid water that's evaporating. So the one with the sock will have a depressed or cooler temperature. And depending upon how much cooler it is, that's an indication of how much water vapor there is. Basically, the more what we call evaporative cooling, the more cooling we have, then that means the drier the air. Dew formation. Dew basically forms when the temperatures have cooled to the dew point temperatures overnight, and that means that dew point temperatures means the temperature you need to reach 100% relative humidity. In other words, the air will be saturated. Oh, excuse me. Adiabatic cooling. Basically, a chunk of air, if you get it to rise, it will automatically expand to those lower pressures. And as it expands, it gets larger. That expansion is work, and that work is paid for by the temperature of the parcel of air. Lifting condensation level, or LCL, that's the elevation you need to take a chunk of air and rise it and cool it adiabatically in order to reach the dew point temperature of that parcel of air. We talked about 4 lifting mechanisms. Orographic lifting, having to do with mountains. Frontal wedging, having to do with cold and warm fronts, cold and warm air masses meeting up. Convergence just means air kind of meeting at one point. Localized convective lifting, here I said the sun kind of creates a hot spot. So I think it was question number 12 in chapter 4. You guys had a question here about 2 parcels of air, parcel of air A and parcel of air B, and they had 2 different dew point temperatures. The dew point temperature of the first parcel of air was 20 degrees Celsius. The dew point temperature of parcel of air B was 14 degrees Celsius. And you were supposed to say at what elevation would condensation begin. So I kind of went ahead and mapped out A here. Notice that for the first kilometer, it's going to cool from 35 to 25. It cools at that dry adiabatic rate of 10 degrees Celsius per kilometer. If we go ahead and go to 2 kilometers, then still cooling at the dry adiabatic rate of 10, it would go from 25 degrees Celsius, it would cool to 15 degrees Celsius. But here, if we revisit what the dew point temperature is, it's 20 degrees Celsius. So notice that actually it's going to go ahead and basically between 1 kilometer and 2 kilometers, which is about 1.5 kilometers, it's going to go ahead and be at 20 degrees Celsius and be at the dew point temperature. So actually that is the lifting condensation level, 1.2 kilometers. Oh, excuse me, 1.5 kilometers. So if we look at the other parcel of air that has a lower dew point temperature, notice that we could go ahead and lift it all the way up to that 2nd kilometer, and it would be at 15. And so here I put the lifting condensation level is actually just a little bit higher than 2 kilometers. The last one, the 3 conditions of the atmosphere. Oh, looks like it all went all at once. So up here where it sees 1, 2, and 3, those are the 3 types of stability, instability of the atmosphere. And in each case, it has to do with what in ELR. Remember, ELR stands for the environmental lapse rate. The ELRs are basically where you send up a weather balloon and it tells you how the temperature is cooling as you go up in elevation. So we say the atmosphere is absolutely stable if the environmental lapse rate, the ELR, is less than the WAR. And remember, and you won't be penalized on the test whether you go with a WAR, the wet adiabatic rate of 5 or 6. Okay, but the atmosphere will be absolutely stable if the environmental lapse rate is less than 5 or 6 degrees Celsius per kilometer. Absolutely unstable or absolute instability is the environmental lapse rate is greater than the dry adiabatic rate of 10 degrees Celsius per kilometer. And conditionally stable means that your environmental lapse rate is actually between your WAR and your DAR. So it must be between 5 and 10 degrees Celsius per kilometer. All right, I know that's a lot in chapter 4. All right, on with chapter 5. So cloud condensation nuclei are important in what I say getting the party started, or basically cloud condensation nuclei get water vapor to begin liquefying. Okay, so we talked about 2 different types of cloud condensation nuclei. Hygroscopic, those that love water, and actually those can begin condensation less than saturation, less than 100% relative humidity. And we talked about hydrophobic cloud condensation nuclei that are actually kind of afraid, or they're water fearing, hydrophobic, and the relative humidity actually needs to be greater than 100% in order for cloud condensation nuclei to begin. So how are clouds classified? I'm going to go ahead and list 3. The 2 are most important. One is what we call form. They're flat or fluffy, stratus or cumulus. The other is elevation. We have low, middle, and high clouds. The low clouds don't have any prefix. The middle clouds use the prefix alto, and the high clouds use the prefix cirro. Then we have precipitating clouds, and they have to have the letters NIMB. So we have 2. We have nimbostratus and cumulonimbus. Those are both precipitating clouds. So form and elevation are kind of what they say, how clouds are classified, but also with regard to precipitation. So the 10 cloud types are here, and I have check marks next to the 10 cloud types. We have like 3 lower ones. They're check marked in purple. And those would be the stratus, the cumulostratus, and the cumulus. Then we have 2 middle clouds, the altocumulus and altostratus. And then we have 3 green checks here are the higher clouds, cirrostratus, cirrocumulus, and cirrus. Then, of course, the 2 precipitating clouds, the low one is the nimbostratus, and then we have cumulonimbus. So 10 cloud types. Cirrus clouds, when somebody talks about a mare's tail cloud, they're talking about cirrus clouds. Lenticular clouds are the ones associated with mountains, and they look like hoverings. They look like bridges. 4 types of fog. We have radiation fog that occurs in the morning as the earth is cooled down. And by the way, for your test, you might want to know kind of a description of each of these 4 types of fog. Hint, hint. Advection fog is basically, the term advect means that air is moving horizontally. So advection fog occurs as a chunk of warm, moist air is oftentimes moving over a cool surface, cools down to the dew point temperature. Advection fog. Advection fog just kind of rolls in, associated with coastlines. Upslope fog, to me, is similar to orographic lifting. Basically, you're using the advantage of basically wind kind of shoving against a slope or a mountain, and the air is forced to rise up, and it can cool to the dew point temperature and create a patch of fog there. Frontal fog, evaporation fog, or steam fog, those are all the same thing. And what they all have in common is basically you have water vapor is kind of injecting into cooler or normal temperature air. So increased water vapor, kind of localized. Supercooled water. Yes. make sure I got all these. Supercooled water is water that is a liquid at a state cooler than it ought to be. So it's a liquid state cooler than freezing. The next one, Bergeron process, is the process of the formation of snow. And I'm not going to ask you any details, but just know that like if snow is forming up in a cloud, we call that the Bergeron process. But we did talk in class that involves supercooled water, and it's kind of a cool process. Collision coalescence, that's actually the formation of precipitation within a cloud. And we said that collision coalescence, it requires an assortment of sizes up there within that cloud of liquid water droplets. And the collision is the fact that we have a collector drop that's moving faster through the cloud than those slow moving liquid particles, and so it collides, and hopefully some of them will successfully coalesce, where that's the gobbling part. The water, the collector drop gobbles up the small liquid particles. Virga, that is basically precipitation that falls from a cloud, but it evaporates back into the air, forms a water vapor before it hits the ground. The next two kind of go together. Temperature inversion is basically as you go up in the troposphere, the air, instead of getting cooler, it gets warmer. And kind of think of it as a pocket of warm air above cold air. And actually, a temperature inversion is what creates the two types of precipitation we talked about in this chapter. Sleet and freezing rain are both require a temperature inversion. Rime is just fancy frost. Fancy frost actually associated with supercooled water. Cloud seeding is we add an artificial cloud condensation nuclei up there, kind of like a crop duster, and try to get condensation started where it wasn't otherwise occurring. The hail suppression, I think you'd be fine if you just simply know that the reason that we are worried about hail and would ever try to modify a hail event is because of the damage it does, and something near and dear to our hearts around here would be the damage it does to crops. All right, on to the last chapter. So reflection is basically we know where the beam of light's going to go. That's reflection. It's the angle of reflection can be anticipated by the angle of what we call incidence. Then we have kind of this a little more random reflection, and the example was if you take a piece of aluminum foil and crumple it up and then kind of smooth it out again, light that falls on that kind of rough surface will reflect, but it will reflect more randomly. Refraction and why it occurs. Refraction is actually the bending of light as it passes from one medium to another medium. And the reason light is bent when it passes from one medium to another medium is because it changes speeds from one medium to another medium. Okay, so here's a figure from your textbook that actually is a picture of the sun kind of low on the horizon, and the sun's light from the sun actually can be refracted or bent if it's low on the horizon, and actually this allows us to see the sun as it is below the horizon because its image is bent up and around, and we see the trajectory up in the sky, but it's really kind of below the horizon. And this we said refraction requires light to pass from one medium into another medium. And so in this case, actually, the refraction is because of the different densities of air. You guys have told me that air is thicker near the Earth's surface, and it gets thinner as you go up. And actually, it's those they behave as two different medium. And so they can cause the refraction of light from the sun. Okay, so mirages, what generally causes them is different densities created by different air at different temperatures. Okay, so there's two types of mirages. There's inferior mirage and superior mirage. So the first one is the inferior mirage, and that's actually kind of like similar to if you're driving down the road and you see basically kind of a, looks like a, and the sun's been out beaming, and basically you see a mirage, kind of a puddle in the road in front of you. That's an inferior mirage. And it occurs because basically you have very hot air above that pavement, that road, and it gets cool quickly. So that is the conditions required for an inferior mirage. Now, two things about an inferior mirage is that it will be below the horizon, and actually their image will be inverted or upside down. So a superior mirage looks like this. Now, I've not seen one of these before, but a superior mirage requires a temperature inversion in place. And the example that your author used is actually if you can have a temperature inversion over over the ocean like this, where basically you have warm water, you have cool water, so the air right above the water is cool, and you can have some warm air kind of move in over that, and of course it continues cool above that warm pocket of air. But that creates a temperature inversion that can create a superior mirage. Now, the thing about superior mirages is that they are above the horizon, and the image is not upside down. The image is not inverted. Rainbows. So here's my little picture of conditions required for a rainbow. And so basically you need to have the sun low on the horizon at morning, or probably more likely in the evening. And then the opposite horizon, you need to have little liquid water droplets. And within those little liquid water droplets, that is where the image of your rainbow is going to appear. So you need to look, have the sun at your back, and be looking at those little liquid water droplets. So I kind of want you to know, or you'll need to know, the thing that happens inside the rain droplet. Now, for the primary rainbow, or the brightest rainbow that we always see, that actually within each liquid water droplet is what we call refraction and reflection off the back of the rain droplet. For that secondary rainbow, this is one of the test questions, you actually have refraction, the breaking down the colors, and then two reflections on the back of the liquid water droplet. So two reflections for a secondary rainbow. And so for the last one, I want you, for these optical phenomenon, these cool things you see in the sky, basically what causes them, either suspended ice particles or liquid water, and then also kind of briefly describe them. So coronas are caused by little liquid water droplets, and halos are caused by ice crystals. And both corona and halo actually can be seen associated with the sun or the moon. The corona, I said, actually touched the sun or the moon, and the halo, there's actually a gap. So on your exam, feel free to draw a picture if you want. Sundogs are caused by, like I said, ice crystals, and sundogs appear as kind of mini rainbows on either side of the sun. And actually, the sun needs to be low on the horizon, just like a rainbow for sundogs too. Sun pillars actually are kind of a vertical pillar of shaft of light extending above or below the sun, and they're caused by sun ice crystals. Glory, this semester I've come up with, and I think maybe a student threw this out, looks like a circular rainbow. And that's what it kind of looks like to me. It's caused by liquid water droplets. So, all right. Best of luck on your tests.